I'd like to welcome you to this recording where we are now really going to start with the curriculum of the MSD 210 module. And we are going to start with a prescribed textbook of Miriam and Craig with Chapter 5. Now, why Chapter 5? Let me perhaps just point out that we are going to do in this module Chapter 4, 5 and 6, and Chapter 8, and then also Appendix B. The reason why we skip over Chapter 1, 2 and 3 is that this covers material that was really discussed in the physics course. Essentially the application of Newton's second law to a particle. And we are going to build further on this foundation that was laid in the physics course. But even though we're going to do Chapter 4 later, we'd like to start off with Chapter 5 because of various reasons, but one of which is that Chapter 5 also revises and further builds on relative velocity analysis. And sometimes in Chapter 4 we need this, and we've experienced that students, even though relative velocity analysis was covered before, that students have a hard time with that. So with this, I'd like to just switch off the video camera of myself here, and I'd also like to change the display into full screen so that you can perhaps see better. The title of Chapter 5 is Plain Kinematics of Rigid Bodies. Now, this sounds perhaps daunting, and because of that I'd like to almost analyze this chapter title a little bit to start off with. Let's look at the end of the title, Rigid Bodies. You may not know this yet, but Chapter 4 deals with system of particles. Now, a rigid body can be considered as a special case of a system of particles. In other words, Chapter 4 really looks at a wider set of entities or of systems. And in Chapter 5 we narrow it down to specifically rigid bodies. Now, what a rigid body is we'll also discuss in a moment. If we look at the title, we see the word kinematics. Now, if you look at your handbook, you'll see that the title of Chapter 4, I've given it here in blue, is Kinetics of Systems of Particles. So Chapter 4 talks of kinetics, Chapter 5 talks of kinematics. What do these two words mean? And that is the next thing that I'd like to focus on. So let's first look at kinematics. Kinematics is defined, and by the way, this definition comes from Miriam and Craig, the handbook. I'm going to use the symbol M&K as you can see here as an acronym for the handbook. Now, in Miriam and Craig in Chapter 2, in specifically Section 2/1, the first section of Chapter 2 on page 21 in both the 6th and the 7th editions of this book, this word kinematics is defined, and the definition given there is basically the branch of dynamics which describes the motion of bodies without reference to the force which either caused the motion or are generated as the result of the motion. Now, what does all of this mean? It means that kinematics is really the study of the geometry of motion. For particles, it deals with the displacements of particles, with the velocities of particles, with the accelerations. Of course, it deals with the fact that the velocity vector of a particle is the time derivative of its displacement vector, and that its acceleration vector is a time derivative of its velocity vector. Kinematics for particles also deals with the trajectories that particles will follow in their motion. Now, when we look at rigid bodies, we can say that kinematics deal with the same things, with the displacements, the velocities, the accelerations, the trajectories of rigid bodies, but there's an additional feature when it comes to rigid bodies, and that is rotation or rotational motion. A particle, one can think of it this way, that a particle cannot really rotate, or the rotation of a particle is not really defined, because a particle is really considered to be an entity with an infinitesimally small dimension set. Its length is basically 0, and its height and its width is 0. And it's just a tiny point. So the whole concept of rotation is not defined for particles. But the moment that one works with rigid bodies, rotation becomes important. By the way, we said that rigid bodies is a special case of a more general case, namely systems of particles. And an example of a system of particle that is not a rigid body would be something like a volume of water or a volume of gas. And when you talk of a volume of water or gas, a fluid or a gas, the concept of rotation also becomes problematic, because yes, there can be rotation, but exactly how is that rotation described? For rigid bodies, the rotation is described quite easily. And rotation is then also a very important property of rigid bodies. And discussing this rotation, or analyzing it, is part of the kinematics of rigid bodies. Thus, for rigid bodies, we'll be considering both linear, and with that I mean in a straight line, or motion along a line. It doesn't need to be a straight line. It's quite often a straight line, but it can also be along a curved line, but without rotation, and rotational displacements, velocities, and accelerations. An important aspect to remember here is that the study kinematics does not involve any application of Newton's second law. If you look at the definition right at the top of the screen, it says it's the branch of dynamics looking at the motion of bodies without reference to the forces which either cause the motion or are generated as a result of the motion. So kinematics don't really deal with forces, and as a result, we do not consider Newton's second law when we deal with kinematics. This is perhaps a hint, because if you need to solve a problem and you know that this problem is a problem of kinematics, then don't even be tempted to try to apply Newton's second law to get to the solution of that problem, because if you know that it's kinematics, you know that it does not involve Newton's second law. Okay, on the other hand, let's look at kinetics. Now, the term kinetics is defined in Merriam and Craig in the first section of chapter 3 on page 119 of the 6th edition, or page 117 of the 7th edition. And the definition given there is, it is the study of the relationship, or the relations, let me repeat this, it's the study of the relations between unbalanced forces and the resulting changes in motion. So it's clear that kinetics has everything to do with Newton's second law. Kinetics is really the application of Newton's second law to a particle, or a system of particles, or a rigid body. So that is the distinction then between kinetics and kinematics. And if chapter 4 then deals with the kinetics of systems of particles, it really means that chapter 4 applies Newton's second law to systems of particles. Now, how is this different from what you've done before? In the physics course and in chapters 1 to 3 of the handbook, specifically in chapter 3 of the handbook, the kinetics of a particle, a single particle, is considered. Chapter 4 then expands that to systems of particles, where you have got more than one particle. How is Newton's second law applied to a system of particles? That is the question that Chapter 4 tries to answer. Chapter 5, on the other hand, does not deal with Newton's second law. It only looks at kinematics, and it looks at a small set of systems of particles, namely the set of rigid bodies. Well, I say it's a small set. It's perhaps not that small, but it's at least a subset of systems of particles, an important subset. Chapter 6, the next chapter in the handbook, will return to the kinetics of rigid bodies, and specifically in planar motion. Now, what is meant with plane kinematics? That is the next thing I'd like to look at. And if we now look at the definition of planar motion or plane motion, that is the motion when all parts of the body move in parallel planes. Now, what is meant by this? Let me try to explain it in the following way, using this picture that actually comes from the introduction to Chapter 5. What we have here is a rocket test sled. It's almost like a motor car, but one that is driven by rockets. As you can see at the back, it's got a driver under a glass canopy here. And this rocket sled runs on, let's say, 2 rails. It may perhaps be more than 2, but for our argument here, let's say it's got 2 rails. One on this side and one on the other side of this picture. Of course, since it's a 2-dimensional picture, we cannot see the rail on the other side. Now, this rocket sled is supported on the rails by these sleds, or I don't know what you would call it, but you can think of this as inside here, there are some roller elements, like small wheels, that reduces the friction, and that allows this vehicle to move forward as the rockets propels it forward. Now, let's imagine that these 2 rails lie in a perfectly horizontal and flat plane. In that case, we can say that that this rocket sled, test sled, is doing planar motion. And the plane in which it's moving, you can think of that as a horizontal plane, because all possible horizontal planes through the rocket sled will move in their plane of definition. If I define a plane or a horizontal plane through the rocket sled, that horizontal plane will stay moving in that same plane as the rocket sled moves along its rails. But I also have an alternative way of looking at this. I can slice up this rocket, if you wish, in vertical planes. I can define a vertical plane somewhere through this rocket sled, and the plane of the rocket, the part of the rocket sled in that plane, will really stay in that plane as this rocket sled moves along the rails. If these rails were to, at some point further on, start to go upwards, to form an incline, then considering the horizontal planes will no longer be valid. The horizontal planes, or considering the motion as in a horizontal plane, will not be valid if the tracks curve upwards, because then the plane, or the part of the sled in that horizontal plane, will no longer be moving in that horizontal plane. But the alternative consideration, where I looked at the vertical planes, that may still be valid, because yes, the part of the sled in the vertical plane will indeed rotate in that vertical plane, but it will still be in that same vertical plane. So if the sled just turn upwards to an incline, the consideration of vertical planes is a valid consideration for planar motion, even though considering the horizontal planes is no longer valid. On the other hand, if the rails of this rocket sled does not make any change in inclination, if it stays in a horizontal plane, but it curves to the right, for argument's sake, in that case, the vertical plane description of this motion is no longer valid, because any part of this rocket sled that's originally in the vertical plane will no longer be in the same plane. It will turn, it will rotate out of that plane as the rocket will turn towards its right, due to the fact that the rails turn towards the right. That is now under the assumption that in that turn the rails do remain in a perfect horizontal plane, that the outside rail doesn't lift a little bit higher as rails are often built. So if there's a turn in the rails, the description of the motion of the rocket sled with horizontal planes through this body is still valid, but the description with vertical planes is no longer valid. Now, if you have a situation where the rails, the inclination of the rail changes, it goes into incline, and then it stays in an incline, and then it goes through a turn, you may be able to approximate the motion with planar motion in separate cases. You may separately consider the case where the rocket sled goes up the incline, and for that you'll use a description using the vertical planes of the rocket sled. And then when it then goes into a turn, you'll have to switch then to the horizontal planar description. But if I make it even more complicated, if I say that these rails will go into an incline, and while doing that it will also make a turn, then I can no longer use this planar description. Then I've got full 3D motion, and the approximation and the simplification that is associated with planar motion is no longer applicable. So I hope that I've explained what is meant by when all parts of the body move in parallel planes. When we can actually use this description of planar motion, it means, or the way that we do this is that we consider the plane of motion as the plane that contains the center of mass of the body. In other words, what we say is that yes, we can think of the body as if each plane in the body moves in its plane parallel to the other planes in the body, but we're going to focus just on one of these planes, and namely the plane that goes through the center of mass of this body. The body then is treated as a thin slab whose motion is confined to the plane of the slab. Of course, it isn't true, but that is the way that we analyze this problem, as if the whole body is just a thin slab. It is as if we reduce this rocket sled or whatever body we're trying to analyze, as if we reduce it to a two-dimensional plane, to a very thin, infinitesimally small slab in the plane of motion. Now, this idealization adequately describes a very large category of rigid body motions, and because of that, it is very useful. And this is really what we're going to do in Chapter 5. All the motion that we're going to, well, not only Chapter 5 and Chapter 6, we're going to consider this idealization where a body can, at least for some part of its motion, be considered to do planar motion, and then we can use the simplifications that are associated with planar motions. Now, when this idealization is not valid, and we will say more about this in the beginning of Chapter 6, but when it's not valid or applicable, it is then necessary to do a full three-dimensional motion analysis. And this is described in Merriam and Craig in Chapter 7. But in this course, in the MSD 210 course, we will not be treating Chapter 7. We will be skipping over it. But let me perhaps just point out that depending on where you're going to end up as an engineer after your studies, it may be necessary for you to actually study Chapter 7 on your own. For instance, I know that in satellite motion, the three-dimensional analysis of motion is very, very important. And hence this topic is very, very important for electronic engineers, because they use satellites in communication systems. and some knowledge of the motion of the satellites is necessary in their field. You'll have to then study this on your own, but at least you'll have a good handbook that you can use for that purposes. Okay, so we've now spoken about plane kinematics. We've looked at kinematics and kinetics. Let's look at rigid bodies. A rigid body is defined as a system of particles for which the distances between the particles remain unchanged. Now, this is also an idealization because no such bodies exist. All bodies on Earth and in space do have some elasticity. If you apply large enough forces to these bodies, they will deform because they have elasticity. So there doesn't really exist something like a rigid body. But at least by approximation, many bodies can be considered as rigid bodies, and especially in dynamics, it really simplifies things considerably if we can approximate a body as a rigid body. So this assumption of a rigid body is usually acceptable if the movements associated with a change in shape of the body under the loading of possible loads are small compared to the movement as a body as a whole, the movement of the body as a whole. So when this requirement can be met, we can use the assumption of a rigid body, and that simplifies our calculations in dynamics considerably. Now, since we will, in Chapter 5 and 6, deal only with rigid bodies, it means that in many ways, Chapter 5 and especially in Chapter 6, when we get back to the kinetics, to the application of Newton's second law, will benefit considerably by using this rigid body assumption. In Chapter 4, though, when we just deal with general systems of particles, we will not be dealing with rigid body systems. Now, let's look at different types of rigid body motions, and this is a table in the introductory section of Chapter 5 that defines different types of planar motion. And the first given here is rectilinear translation. This is shown in these two figures. It's a certain body, this blue bean-shaped body, with a line AB, 2 points A and B, on this rigid body, which are connected with a line. This body moves so that after a while the body is in the position as indicated by this dashed lines, and the point A is moved to the point A accent, the point B is moved to the point B accent. And what we see is that during this whole motion, the orientation of the line AB did not change. The fact that it didn't change identifies this motion as translation. It's, whenever you have the situation that all lines on the body remain in their original orientation, the motion is described as translation. Now, this is rectilinear translation because of the fact that all the points in the motion moved along a straight line from the original position to the final position. If all the points move along straight lines and the orientation of any fixed line on the body remains constant, we have rectilinear translation. An example of this is indeed this rocket on the test sled that we've discussed earlier, provided, of course, that these rails are, the two rails are in a single plane, in a flat plane. The second category is that of curvilinear translation. If we look at the same two bodies, we see that the orientation of the line AB did not change through this motion, but the trajectory of point A is not a straight line, it's a curved line. And likewise, the trajectory of point B is also a curved line. So this whole body followed this curved trajectory, but in this whole motion, the line AB and all other lines for that matter in the body remained in their original orientation all the time. This is then called curvilinear translation. And an example of that would be this blue rectangular box that is suspended by two bars of equal length, which is suspended from something like the ceiling with 2 hinges at the ceiling and also 2 hinges at the bottom. So this rectangular box will swing below the ceiling in a way that each point on the box will move along a circular trajectory. But the box itself will not rotate. This vertical line will always stay vertical. This horizontal line will always stay horizontal throughout the motion. And any line on the box will remain in its original orientation throughout this motion, even though any point on the body will follow a circular arc. So this box, this blue box, will then be doing curvilinear translation, specifically in a circular trajectory. By the way, the 2 arms are not doing this motion. We'll be getting back to the motion that the arms do in a moment, but specifically the box at the bottom does curvilinear translation in this motion. The third category is that of fixed axis rotation. Let's say I've got the same body with points A and B, but in the second configuration, when the body occupies the space with the dashed lines, we see that point B is moved from B to B accent, but point A has not moved. And we also see that the orientation of the line AB has changed to that of the line AB accent. And there's an angle theta between these 2 lines. So this is a case of fixed axis rotation. Rotation about the fixed axis. In this case, the fixed axis is through the point A. Of course, I think the distinction between this and the 2 cases of translation that we had at the top is quite clear. An example of this is a compound pendulum. Please also note that you can have fixed axis rotation about an axis that does not even go through the body. It's quite possible that the point of the fixed axis of rotation could have been sitting somewhere at the top here, and in that case the point A would also have moved along a circular trajectory just like the point B. So for fixed axis rotation, it's not a requirement that the axis of rotation should actually be intersecting with the body. And then the last category is that of general planar motion. If we look now at the 2 bodies, we see that the point A has moved along a circular trajectory, not circular, a rectilinear trajectory to A accent, and B likewise have moved along a rectilinear trajectory to B accent, and also the line AB has changed in orientation. So this is general planar motion. It's the most general case of motion that we can have, and you can think of general planar motion as really a combination of fixed axis rotation and translation. It is true that during general planar motion, for a very small instant in time, if I break up this whole motion into a whole set of small motions through very small, infinitesimally small time steps, for each of those time steps you can consider just during that time step the motion as fixed axis rotation. In other words, there's what is called an instantaneous center of rotation for each of those time steps. But if that instantaneous center of rotation for each of the time steps is not the same for all of them, I do not have fixed axis rotation. On the other hand, if it's possible to say that this instantaneous center of rotation is in fact the same for all the time steps, then the motion is not general planar motion, but then it is actually fixed axis rotation. So you can think of general planar motion as if it is a sequence of an infinite sequence of fixed axis rotations, but where the axis is actually not fixed, but the axis also moves with time. Now, an example of this general planar motion is the motion of the connecting rod of a reciprocating engine, like your motor car's engine. This would be the piston, and if the motor car is stationary, the piston will be doing rectilinear translation. It will be moving back and forth in a straight line, this line at the head of the piston will keep its original orientation all the time, and all the points on the piston will just move in straight lines. So the piston will do rectilinear translation. This here is the crankshaft. The crankshaft rotates about this axis, and so the crankshaft will be doing fixed axis rotation. But the example here is really that of a connecting rod. The connecting rod connecting the piston with the crankshaft. This connecting rod will be doing general planar motion. It will have a component of rotation and a component of translation as the crankshaft turns and the piston goes up and down. Of course, when the vehicle is not stationary, the moment the vehicle starts to move, and depending on the way that the engine is mounted in the vehicle, and depending on the movement as to whether the vehicle goes around a circle, you can then say that in that case, the connecting rod will be doing general planar motion, but even the crankshaft and the piston will be doing general planar motion, because both of them will also translate and rotate. Now, when we look at rotation, an important identity is derived in a section in the introductory chapter of chapter 5. Let's consider a rigid body that is rotating in a plane. And let's consider two lines on that rigid body in the plane of motion. The line 1, indicated in red here, and the line 2, also indicated in red. And let the angle between these two lines be given by the angle beta. Now let's say initially the body is in orientation such that the angle between line 1 and some other fixed reference is theta 1, and the angle between the line 2 and the same fixed reference is the angle theta 2. Of course, since this is a rigid body, the angle beta is invariant in time. It cannot change. If it could change, it would not have been a rigid body. The angle beta is invariant due to the fact that this is a rigid body, and these lines are part of this rigid body. We can now say that just from pure geometry, the angles here, that theta 2 is equal to theta 1 plus beta. Now, having written this, we can take the first time derivative of this equation, and if we do, we see that the time derivative of beta is 0 because beta is invariant. And we then come to the conclusion that theta 2 dot is equal to theta 1 dot, where the dot above the symbol is the notation that we use in dynamics for the first time derivative. A single dot above a symbol indicates a first time derivative. So we see that the angular velocity of line 2 is the same as the angular velocity of line 1. We can also take the second time derivative of this equation, and if we do, we get theta 2 double dot is equal to theta 1 double dot. So this equation tells us that the angular acceleration of line 1 is the same as the angular acceleration of line 2. Or we can do a small increment of this equation. If we do a small increment, we say that the small increment in theta 2 is the same as the small increment in theta 1 because there is no increment in beta. So this leads us to a very, very important conclusion. I'd like to warn you about this. I've seen many times that students forget this, and when they forget this, they are no longer able to solve some of the problems that we will be giving you in this course. So always remember this identity, this property, that all lines on a rigid body in its plane of motion have the same angular displacement, the same angular velocity, and the same angular acceleration. Now, let's quickly look at some mathematics of rotation. The rotation angle will be the angle theta as we have it on this sketch here. You can think of a rotation angle theta. The first time derivative of the rotation angle, which we also indicate with theta dot, that is the angular velocity, in this case as a scalar. We're also going to deal later with angular velocities as vectors, but here it's just as a scalar quantity. Then we can take the first time derivative of the angular velocity, as a scalar, and we indicate that as omega dot, but we call this alpha, the angular acceleration, also as a scalar. Or you can say that the angular acceleration, of course, is the second time derivative of the angle of rotation. Now, having said that, we can express this derivative d omega dt using the chain rule as d omega d theta times d theta dt. And d theta dt we see is the same as omega. I mean, that is what was defined at the top here. So this tells us that alpha can be expressed as the derivative of the angular velocity with respect to the rotation angle times the angular velocity. This in itself doesn't seem very meaningful, but if we now multiply this equation with d theta, we end up with this equation. This is just another way of expressing the same equation. And this is very important because it says that omega times d omega is the same as alpha times d theta. And this expression can be used to construct an integral, which will then say that the integral of angular velocity with respect to angular velocity is the same as the integral of angular acceleration with respect to angle. And this integral will quite often be used later on in Chapter 5 and then also in the solution of dynamic problems in Chapter 6. By the way, all these equations are equations 5.1 in Merriam and Craig. Now remember, in school you derived the constant acceleration equations. Familiar equations, I don't need to repeat them, but they are, by the way, derived through integration. Perhaps I should say re-derived through integration, because perhaps at school you didn't use integration to derive them. So it may be actually useful for you to go back to Merriam and Craig, Chapter 2, Section 2. That's on page 25 in edition 6 and in edition 7, and observe how these three equations are actually derived through integration, since you now know how to integrate. But that's not the point I'm trying to make here. The point I'm actually trying to make is that when we talk of rotation, we have similar constant angular acceleration equations. By the way, remember that these three equations are valid only if the acceleration a is constant with time. In the same way, these three equations are valid only if the angular acceleration alpha is constant with time. But you can see that these three equations are the equivalent equations of these three. They really are derived in the same way. The only difference between these three and these three is that these equations deal with rotation as opposed to these dealing with linear motion. And these three equations are, in Merriam and Craig, the unnumbered equations below equation 5.1. That's on page 334 in edition 6 or page 328 in edition 7. Yeah, so that brings me to the end of this recording.